Thank you for returning back to this course. You can find the content at blogs.umbc.ca/cognition. Let's explore Module 2.2, Perceptual Paradigms. As we begin this new module, 2.2, we're going to revisit a theme that has already come up, and that is that perception involves active bottom-up and top-down processing. We're also going to introduce a new theme as well, and that there's a debate regarding the degree to which we can add or distort information in the proximal stimulus. Our learning outcome will be to focus on explaining the three paradigms for studying perception and the differences between constructivist and direct perception perspectives. Here's our roadmap for this section. We'll begin by exploring the information processing approach, and we'll examine the bottom-up, top-down theme. We'll then move into Connectionist Approach, and finally we'll wrap up with the ecological approach. The information processing approach is a classical approach to studying perception and cognition. This approach assumes that sensory information is analyzed in a series of stages. We go from the components working up to the whole. We're going to start by examining information processing models that assume a bottom-up approach. By that we mean that we're going to start with small bits of sensory information, which are then combined to form a percept. Let's explore two bottom-up theories of perception. The first, template matching theory, states that every stimulus is compared to a previously stored pattern or template. So you can think of your barcodes on food products. When they get scanned in, that barcode is then matched to a template or a previously stored pattern so that they can then associate a price with that particular product, as well as other information. The issue with template matching theory is that if we take, for example, everyone's written version of the letter A, your version is going to be different than mine. So how many templates do we need to have for us to be able to recognize common repeating patterns, especially when there are differences, physical differences, in how they're presented to us? So that line of thinking led to feature analysis theory. Within my handwritten version of the letter A and your handwritten version of the letter A are going to be common features. So feature analysis theory states that perception is the result of detecting patterns on the basis of a collection of individual features. So for example, in a capital A, we've got two straight lines that come together at a point at the top, and then one horizontal line somewhere near 2/3 of the way up the legs of the letter. Feature analysis theory can begin to explain how we can account for individual differences across patterns that we see in our natural world. Let's explore more. I'll provide a visual description of the pandemonium model in just a moment, but the pandemonium model is essentially a feature analysis model that works on the recognition of letters. It starts by having feature detectors, then those feature detectors go together to form letters, and at some other level there's a decision. This letter versus that letter was shown. We can extend that line, building from letters up to words, which are combinations of letters. Letters and words aren't the only things that we need to recognize in our environment. More importantly, we need to recognize a lot of objects. Objects are comprised of features as well. Biederman calls these geons, basic geometric shapes. Those geons are combined in different ways spatially so that we can then recognize the form of an object. Now, although I've put recognition by components under this category of feature analysis theories, it is important to note that there are distinctions between Biederman's recognition by components and feature analysis theories. In particular, they emphasize different structural ways of analyzing information. In 1959, Selfridge published an article in which he described a particular model, a feature analysis model. This model he called Pandemonium. He had a few demons in his model. He had some data demons, some computational demons, cognitive demons, and a decision demon. Essentially, what happens is that these demons shout, and the loudest one, the one that shouts the loudest, the strongest, gets most of the attention. So you have data. This is when we encode the visual pattern. So we encode a letter A, for example. That information then is fed up to the next level, in this case the computational demons, where parts of the data are matched to particular features. So simple features such as lines, circles, curves, etc. Those features will shout the loudest if they match with features found in the encoded pattern. Now, the features that shout the loudest then get to send their input on to the cognitive demons. And what the cognitive demons try to do is synthesize the different features, bring together all of this noise into the identification of a particular letter, such as A, for example, if there are two slanted lines in a horizontal line that are strong components found in the original data. So let's briefly review this model. From the external world, we encode the pattern that we're interested in. That pattern is then broken down by the cognitive demons into specific features. Now, thinking about letters, there are only a handful of features that could be broken down into. Those features, whichever ones shout the loudest, then are combined at the cognitive level to have a mental representation of a particular letter that existed in the real world. So similar to feature analysis, the recognition by components also assumes that we break down the information into its constituent parts. So let's take a look at a schematic of a lamp. This lamp is broken down into 4 geons. We have a circle geon, we have a cylinder, a square, and a tube. These are the 4 geons that would constitute the image that we see on our left. Feature analysis models aren't without their problems. One of the concerns that has been raised is the question of how many features are necessary to represent all of the patterns of a particular object that we see in the world, or of different handwriting types, for example. How is it that we get those mental representations for features originally? How do we acquire them? So we've still got a lot of questions, but this certainly does reduce the memory load on our cognitive systems compared to the template matching models that we discussed earlier. Okay, so the models that we've talked about so far have all been bottom-up models of processing, of cognitive processing. That is, we take information that's derived from the stimulus and we use that to build up to a particular mental representation. The issue associated with bottom-up processing is that it doesn't allow for context effects. Conceptually driven processing, or top-down processing, is driven by higher level knowledge. For example, memories of past events. Let's now look at a couple of context effects so that we get an understanding of how conceptually driven processing might occur. Let's look at the first example, the cat. Notice anything similar about the two words? Yes, the second letter in each word. They're identical, but in the first word, we're reading T-H-E. In the second word, we see it as C-A-T. Yet the A is very similar in structure. In fact, it's identical to what we saw presented as an H in the first word. How is it that we read these two sets of words as the cat? Context. Let's again look at another example. Example B. Here we've got a string of letters and a string of numbers. In the context of letters, we have A, B, C, D, E, and F. In the string of numbers, we have 10, 11, 12, 13, and 14. Notice anything the same about these two? You've guessed it again. That is, the B and the number 13 are physically identical. Yet, we don't see that when we're reading a string of letters. We don't see a number 13 there, we see the letter B. And when we read the string of numbers, we don't see a letter B, rather we see a number 13. This example illustrates the importance of context in how we interpret information that's presented to us. Okay, so far we've explored the information processing approach. We also brought in the nuance of bottom-up and top-down processing. Now we're ready to move on to the connectionist approach. As we've talked about before, the connectionist approach is a neurally inspired approach for cognition. That means we look at the brain, how the neurons operate, or how we think they operate, and we've developed a connectionist type model based upon some analogies to the principles we see in the brain. So for example, we're starting with a real brain. We understand how information flows from one part to another part, and then what we try to do is we try to develop what we call a conceptual brain. From the conceptual brain, we've then developed something that's a little more refined called the connectionist model. Our connectionist models often have 3 layers, though they don't necessarily have to have 3 layers of input. They have a input level, hidden level, and an output level. Let's explore 3 components of connectionist models. Connectionist models are layered. We go from an input units to hidden units to output units. The connection strength between those units is modifiable. Often the connections within a layer, so within the input layer for example, are inhibitory. Connections between layers are excitatory. So one layer will feed excitatory information to the next level. Here is a schematic that I've drawn for a connectionist model. Stimuli are received by the input units. Those little circles there are nodes. Those nodes get activated. And if a particular node, such as the one at the top of the input layer, gets activated, it's going to send inhibitory information to the rest of the input units. That information is also going to percolate to the next level. So the input unit at the top there will feed the hidden units with excitatory information. Each node is connected with every other node in the network. Then the hidden units, when they get excited, are going to feed excitatory information up to the output units. The output units are where we collect the responses. This image depicts McClelland and Rumelhart's 1981 classic connectionist model for word recognition. The input layer is represented by features. When those features are activated by the stimuli, they feed forward to the letter level. At the letter level, there are inhibitory connections between the nodes within that particular layer. So if you look closely at this image, from A to N is a connector. These connectors have little circles at the end. That's one way of representing an inhibitory connection. Let's say that the letter A is active. That letter feeds up to the word level. So it's going to feed excitatory information to the word able, for example, to trap, to take, and to cart. You can see that they have a diamond shape end to these connectors representing excitatory connections. You'll also notice that from the word able back down to the letter A is a excitatory connection. So there's both feed forward information going from the bottom, and we can account for context effects in this model because information comes from the word level down to the letter level. we've briefly explored information processing and connectionist approaches to perception. Both of these approaches assume that the perceiver acts upon the proximal stimulus, that is, the image on the retina. That information is added. It's added from our long-term memory stores. This view of perception is called a constructivist approach to perception. That is, we take information from the proximal stimulus and we add information from long-term memories to construct a percept. Let's now explore the ecological approach to perception. This approach lies in stark contrast with the information processing and the connectionist approaches to perception. It's associated with J.J. Gibson. J.J. Gibson stated that perception involves the direct absorption of information present in the environment. Essentially, he was saying that we do not add any information to the stimulus because the stimulus itself is so rich. It doesn't need further processing or interpretation. Here are a couple key points. Gibson argued that perception was the result of stimulation, that there was no need to create an internal mental representation. A second key point is that people do not just perceive objects, they also perceive the affordances that an object has. Let's explore that in a little more detail here. Can you picture a chair? When you see a chair, what does it afford you? It affords sitting. Despite the fact that we have a multitude of chair shapes, sizes, designs, from a beanbag chair to an office chair, we can all sit in chairs. So when we perceive, we not only perceive the object, but also what we can do with the object, what it affords us. Okay, now we're ready to wrap up this section. So in summary, perception, like cognition in general, can be viewed from many perspectives. We've talked about the information processing approach, the connectionist processing approach, and the ecological approach. The differing perspectives have all added to our understanding of perception. Today, cognitive psychologists are developing theories that often integrate two or more of these perspectives.